right, a nice introduction. Okay, we're going to work a little bit with integrals. And in Chapter 7 and 7.1, what we're going to be looking at is different types of integration techniques. Okay, so to begin with, we're going to look at some U-substitution examples. And kind of the key thing on this is when you do, if you choose U, you want to choose it in such a way that du, the derivative of U, is either going to be the remainder of the integrand, that's the part you're integrating, the function you're integrating, or it might be off by a constant. That's not always possible, and U-substitution doesn't always work. So we're going to look at some examples where U-substitution does work. So let's take a look at this one. Now, whenever you're doing an integral, you got to kind of know where you're going with these. One of the things that I see a lot of times on a problem like this is a basic thing that I know is if I have 1 over u du, that's equal to the natural logarithm of the absolute value of u plus c. Okay, like that. So when I see an x in the bottom, that's kind of what that begins to make me think of, is maybe we got a natural logarithm. So what I'm going to try to do here is I'm going to try to let u be equal to ln of 2x. And sometimes you just have to try something, and it isn't always going to work. So if it doesn't work, try something else. Okay, so now the next technique is take the derivative of u. And this is a chain rule, so remember if you're doing the derivative of ln of 2x, by definition that's going to be 1 over the function times the derivative of the inside function 2x, so that's going to be 1 over 2x times 2. That crosses out, that leaves you 1 over x. Okay, so the derivative of this is 1 over x, and don't forget to put your notation dx like that. So this is a pretty straightforward U-substitution problem. Right, so now what we're going to do is I'm going to use a highlighter to kind of show this. This part right here is going to be replaced with u. Okay, this part right here, dx over x, is going to be that part right there. So see, everything is accounted for in this integral then. Okay, so this is where your u is going to go, and then that's where your du is going to go, like that. Okay. So what you end up having then is you end up, when you write your u integral, what you're going to end up having is the integral of u, and then that's just u, and then 1 over x dx is the rest of the integral, so you're going to have u times du. Okay, now this is a basic power rule, so remember if we have a power rule, for an integral, what we do is we add 1 to the exponent, divide by that exponent, and then you have your arbitrary constant c. Now you want to plug back in now. U is ln of 2x, so that thing is going to plug back in right there. So then you get ln of 2x squared over 2 plus c should be the answer to that integral then. Okay, so that is the answer to the problem. Now, one of the things you want to, be pretty confident in doing on problems like this is be able to verify that you're right. So I'm going to do that on some of these problems. Let's just check. So if we were to go through and do the derivative of ln of 2x squared over 2 plus c, okay, what you would do is by chain rule, what you would have this derivative of this piece right here, well, you got a constant 1/2. That's the 1/2. And then chain rule, you're going to bring the 2 down, leave the ln of 2x alone, subtract 1 from the exponent, and you're going to multiply by the derivative of what's inside. The derivative of what's inside is 1 over 2x times the derivative of 2x, which is 2, and then of course the derivative of the constant is 0. So what you have is the 2's are going to cross out. That's going to leave ln of 2x to the first times 1 over x. So that's going to be ln of 2x over x. And that's basically what we were integrating on that problem then. So that's how you can check and verify the answer. Okay, if you look at this thing right here, see that thing takes you back to the beginning. Okay, that's the same thing. All right, so that is a standard U-substitution problem. That's a very basic one, kind of a elementary level problem. Okay, next thing I'm going to do is move on. Now we're going to do a definite integral. And in a definite integral, we're evaluating from 0 to 3 pi over 8, so you're going to be using the fundamental theorem of calculus to evaluate that. Now, one of the things I went ahead and did on this problem is I went ahead and put this in my graphing calculator. So I'm going to just kind of show you how I'm going to do that for you here. And you can do this along with me if you want. Okay, so I'm going to put in, you want to make sure a couple of things when you're doing this. You want to make sure that you're in Radian mode. Okay, so you want to be in Radian and function mode. Then we're going to put in the sine of 2x minus pi over 4. Okay, like that. And for the window, since we're integrating from 0 to 3 pi over 8, that's what I'm going to do is I'm going to put in 0. Then I'm going to put in 3 pi over 8. Just use the pi key. Okay, like that. And you can, let's just increment it maybe by pi over 8. It doesn't really matter. Okay, like that. So we got that. Now for the y's, we know the sine has a max of 1 and a min of negative 1. So I'm going to just put in maybe negative 2 to 2. And then I'm going to scale that by 1. And then let's do a graph. So I'll type the graph button. Okay, you don't have to do this, but I think it's a graphing calculator can kind of help you see pretty clearly what's going on. So I'm going to close my calculator just for a minute and push that to the side. And we're going to go ahead and work out the details, but what we're doing is we're finding the area from 0 to 3 pi over 8. I've got this kind of set up as that's pi over 8, 2 pi over 8, which of course is pi over 4. Then we got 3 pi over 8. Going up to 2 and going down to negative 2. So we're looking at the area under the curve. Now some of that is going to give you some negative, that's going to be, that part of the integral is going to evaluate as negative, that part's going to be positive. So the value of this integral is going to be adding those two regions together. Okay, so first of all, this is a U-substitution problem. About all you can really do when you look at the form of this thing, you know that the integral of the sine of x dx is equal to negative cosine x plus c. And the reason is because if you take the derivative of negative cosine x, well, the negative is a constant, the derivative of the cosine is negative sine x, so that will give sine x. Okay, that takes you back like that. So what we are going to work with is try to change this into a sine of u integral somehow. So what I'm going to do is I'm going to start by letting u be equal to 2x minus pi over 4. Okay, then du will be the derivative of this, which is 2 dx. Okay, all right, so we got that kind of absorbed. Now, we'll end up having the sine of u, but all we have left over is a d of dx. So see, this thing is going to be u. The rest of this needs to be du. So this is off a little bit. So what I'm going to do is divide by 2, or multiply both sides by a half. So I end up getting 1/2 du is equal to dx. Okay, so this is how everything plugs in. That's u, and then dx is 1/2 times du like that. Okay, the other thing is, since we're working on a definite integral, is we also would like to go through and change these limits of integration. So I'm going to do u like this. I'm going to do u is equal to 2, and I'll plug in the 0 there, 2 times 0 minus pi over 4. So if you work that out, that gives negative pi over 4. So that's what this limit of integration is going to change into, negative pi over 4. Then we're going to do the same thing for the upper limit. Okay, so we're going to take that U-substitution So we're going to do u is equal to, remember we're doing 2x minus pi over 4, so we're going to do 2 times 3 pi over 8 and minus pi over 4. Okay, so that's going to reduce down to this. That looks like that is 2 over 8. That's going to reduce to like that. That's going to be 3 pi over 4 minus pi over 4, so that's 2 pi over 4. Okay, so that's going to be pi over 2. Okay, so that limit of integration right there is going to be pi over 2. Okay, like that. Okay, so now we're ready to set it up. Okay, so we got kind of all that U-substitution stuff going on here. So here's how we go. We've got the integral, the 0 changed to negative pi over 4, the 3 pi over 8 changed to pi over 2. Okay, this is going to be sine of u. Okay, that's what we let u be. And then the dx in here is going to become 1/2 du. Now, since the 1/2 is a constant, you can put that in front like that. So that's what we're going to work out, which is a pretty simple integral now to do. Okay, so what we're going to have is the integral of the sine is negative cosine u. And we're going to evaluate that. And don't forget about the negative 1/2. We got the negative 1/2 I need to put in there in the constant. So I've got negative 1/2 cosine u. And then we're going to evaluate that from negative pi over 4 to pi over 2 like that. Okay. Now the fundamental theorem, when you have a constant, you can just bring that constant out. The fundamental theorem says to evaluate the upper limit of the antiderivative. So we're going to do cosine pi over 2 minus, the fundamental theorem tells us to do that, cosine of negative pi over 4 like that. Okay, now once we get that put together, then we can just evaluate this based on a unit circle. So negative 1/2. Okay, you can kind of look at these things on a unit circle if you want to. At pi over 2, you have the point 0, 1. The cosine's the x value, so that's going to be 0. Okay, at negative pi over 4, you're down clockwise at 45 degrees. That's the point square root of 2 over 2, negative square root of 2 over 2. Like that. So the cosine's the x value, so that's going to be square root of 2 over 2 like that. Okay, so now we have negative 1/2 times negative square root of 2 over 2. So it looks like the answer to the problem is positive square root of 2 over 4. Okay, so that will be the answer. Now the thing that you can do on a definite integral a lot of times is you can check your answer with some technology with your graphing calculator. So what I'm going to do on this, since I've got the graph up here, I can go second calc. I can go to option 7. Press enter. Now the lower limit, now we're going back to the original integral, not the U-substitution integral. We had a lower limit of 0. Press enter. Upper limit was 3 pi over 8. All right, and we do that. Uh-oh, must have put something in there wrong, so let me try that again. Okay, the upper limit, 3 pi over 8. Let me make sure I got my window set up okay. I think I do. Okay, what I'm going to do, since the calculator is getting an error, what it's doing is that upper limit, when I set my window, it needs to be a little higher. So instead of going to 3 pi over 8, let's just go out a little higher. Let's go like 4 pi over 8, like that. And let's graph it, and then we'll do the integral, and I'll show you that we have the right answer. Okay, so it's graphing that. Okay, now I'm going to go second trace to open the calc menu, go to option 7. Lower limit is 0. Upper limit and the integral is 3 pi over 8. I think it'll work now. Okay, now it should shade the region. Okay, now notice it stops at, stops at 3 pi over 8 right there. So that is about approximately 0.35355,339, if I'm seeing that okay. Now if I clear that, And if I take our answer was square root of 2 over 4. Get the same thing, so we're right. So we can use that to approximate that area, okay? Okay, so that will be the end of the first part of this, and I'm going to kind of do videos in sections on this.